To Waidsum Academy. Today we are in Physics chapter 10, and our today's topic is the transfer of thermal energy. The transfer of thermal energy. Without much ado, let's begin. Now, in this chapter, there are basic things we're going to look at. You can see pigwee, right? You see pigwee. We observe the body covering. We say, first of all, here are some questions you see or you can ask yourself. We say, observe the body covering. Body shape, body size, and behaviors of pigwees, and discuss how these pigwees have adapted for a very cold climate. How they have some characteristics that enable them to be able to adapt to very cold climates. Okay, and then another thing is which other animal lives in the cold countries and how they are adapted to this kind of cold temperature. Now, how do Arctic explorer or skiers protect themselves in ice weather? So these are some of the things we want to look at in this chapter that will help us to give a very good understanding. Here are some learning objectives. One of it is to describe the thermal conductions in solid, and then the other is to describe the thermal conduction in bad, why the thermal conduction is bad in gas and liquid, or liquid and gases. Now, quickly, let's take an overview of what we have. The 10.1 is the transfer of thermal energy. Here we look at the heat transfer in solids, and probably, yes, heat transfer in solids. 10.2, we look at heat transfer in liquid and gases. So here we're going to know the thermal energy transferred from a region of higher temperature to a region of colder temperature or lower temperature. So without much ado, let's take a look at the everyday experiment, something we can use to verify this concept. Why does an object feel hot or cold? Why? Because of the transfer of thermal energy. Object feel hot or cold due to the transfer of thermal energy. So remember, heat energy is being transferred from a higher region to a colder region, okay? Higher temperature region to lower temperature region. And the difference in temperature equal to the net flow of thermal energy. The difference in temperature from higher region to the lower region equals to the thermal energy of the surface or substance. Now let's quickly take a look at a small experiment. We take 3 buckets and we fill them with water at different temperature. We have P, Q, and R, and the P temperature, we set temperature at 10 degrees Celsius, Q at 37 degrees Celsius, and R at 50 degrees Celsius. So the first thing we do is to prepare these 3 water, label P, Q, R, and at this temperature respectively. And then the next is to place both of our hands in the in Q. We put our left hand and right hand, we put them in this 37 degrees temperature. So, do we feel warm or cold? No, we don't feel warm or cold when we put both of our hands here. Why? Because the temperature of this bucket of water is almost similar to the temperature of our body. So the heat is at equilibrium. There is no thermal flow. There is no heat transfer from the body to the bucket of water, or from the bucket of water to the body. So there's equilibrium. We are at equilibrium. So that's why when we put our both hands, we don't feel hot or we don't feel cold. But however, the next thing, we place one of our hand on the left side, which is 10 degrees Celsius, and we place the other one on that, which is 50 degrees Celsius. Now, one will feel hot, one will feel cold. The one on R will feel hot because the temperature of this place is greater than the temperature of our body. So there's net flow of heat energy from this bucket. There's net flow of heat energy from this bucket to our body. So there's thermal transfer, okay, from this bucket to our body, because temperature here is higher than temperature of our body. Now here, the body will feel cold because our body we transfer energy from our hands or from our body to this water, to this bucket of water. So hence the body will feel cold because heat energy at 37 in our body will flow into the next one is to quickly look at 10.2, which is conduction. Okay, conduction is happens because of, and number 2 is the transfer of free mobile electron. The other one is free mobile electrons that carry the thermal energy from one spot to another. Okay, so that's how conduction happens. Now, how good are different materials at conducting thermal energy? How good are different materials? Okay, to do this, we have to do a little experiment like we just talked about. You hit one end, there you have what we call the hot region. the region where you provided the bossy burner, where you hit it. This is a metal. This is a metal. And then you put a candle wax, you melt it, and use it to stick a pin to it. You stick a drawing pin to this metal with thermal energy. There's a lot of thermal energy. Vibration. TTIICE. Lattice vibration. The particle vibrates. And then plus the free mobile electrons in this metal. Free mobile electrons that carry the heat energy from one spot to another to this cold region. Okay, so the heat flows here. Now from this region, we have best conductor. Where you hit it, this is where the conduction is the highest. And this region that is still cold or considered cold region, the heat energy is considered the lowest. Is considered so here will be the worst conduction. Here will be the best conduction. Okay, for different materials. Okay, for different materials. Now, if you have diamond, copper, steel, ice, polythene, fiberglass, polyester, and worst insulator is highest on this side. Insulator is highest on this side when you have air, polystyrene, fiberglass. Insulator is highest here and worst here. Okay, so that's for this one. Let's move to the next one in terms of conduction. How good different materials. Here we want to explain how good different materials are at conductive thermal. Here we have to take different material. We have to take copper, aluminum, steel, and probably a glass. We heat all of them together. We can carry out an experiment and heat all of them and see which one conduct faster. Okay, now let's take a look at this, an experiment. The experiment is to investigate the transfer of thermal energy through solids with different conductivity, right? Now, like we said, you melt a candle wax to stick a drawing pin to one end of it. This is a bossy burner, okay? And then this is a triple stand. You suspend them in a triple stand and heat all of them. You connect them to the bossy burner heat. Connect them from one end to the bossy burner. The other end, you stick a drawing pin to it, to all of them. And then you heat. So we record time it takes for this pin to fall off. You know, when the heat reach here, it will melt the candle wax and the pin will fall off. The pin, when this one is melted, the pin will fall off. When this candle wax is melted, the pin will fall off. When this candle wax is melted, this pin will fall off. So what it means is that we record the time fall off, the time it takes for the pin attached to the glass rod to fall off. Now what it means is that now the one which is considered the hotter region, the heat will flow to this side. Now if you are the most conductive, heat will flow fastest to reach the other end. When you reach the other end, the wax will melt and the pin will fall off. Okay, so this is how you report. You describe the explanation. It's faster here. You may not put the values for time, but you already explained in the discussion aspect that the time is shortest for copper because thermal conduction is fastest in copper compared to aluminum, and then next to steel, and then it's worst off in glass rod. Okay, now let's move to the next thing. How does conduction work? How does it work? Okay, I think literally we've explained this already. We can look at, let's start with metals. When you hit a metal has two things happen in metal. They have free mobile electrons to carry out the vibration, and then the particle vibrate, leading to what we call lattice vibration. So as the particle vibrate, they move the energy, and the free electrons also get heated up. They move this thermal energy from the hotter region to the colder region. So the thermal energy is transferred from one side of the metal to the other. So it takes time for them to feel the heat. It takes longer time. Okay, it happens a long time before the heat is transferred from the hotter region to so they are considered poor conductor, which is what you call insulator. They are considered poor conductors or what you call insulator. Now let's move on to the next slide. Now, why is the rate of conduction much faster in metals than in non-metal? We already explained that, right? Because metals have two things. They have free mobile electrons, which is very important. They have free mobile electrons, which helps to carry the thermal energy from the point where you're hitting it to the other side where that doesn't get the heat. And also they have lattice vibration. Non-metal do not have free mobile electrons. They only have the lattice vibration, and they don't have so it takes longer time for non-metals to activate or to transfer the thermal energy from one spot to another. Now let's move to the next slide. Now here we are asking, why are liquids and gases bad thermal conductors? Why are liquid and gas? Okay, liquid and gas, the particles are not fixed. They are not in fixed positions. Okay. Thermal energy can also be conducted from hot regions to colder region in liquids and gases by conduction, but it's not efficient, right? Why? Because the particles of liquid and gases, they space further apart from each other. They've spaced further apart, or like that of solid that are fixed in fixed position, they're very close together. So collision between the particles in liquid and gas is less frequent. The collision is less what? Frequent. There's less frequent collision between the particles. There's less frequent collision between the particles. The particles are spaced further apart. So when one region that gain the kinetic energy, before it can transfer, it takes time. It takes time because the particles are not in contact, directly in contact with each other. It takes time for it to get to the next particle and so on and so. So the whole process is slowed. The whole process is slow. So that's why they are not good. They are bad thermal conductors. They are not good thermal conductors, liquid and gases, compared to that of solids. Now here are some less practice questions. You pause this video at these junctions and you solve this question. How is thermal energy transferred? How is thermal energy transferred? Okay, we can talk about conduction, convection, and radiation, right? So why is copper a good material for making cooking pots, right? Because it's made up of particles that are very close together, and they have free mobile electrons to carry out the thermal energy from the point of heating to the other point where the heat is not there. So you pause and answer all of these questions. Now let's go to 10.3, which is convection. Okay, convection. Convection normally happens in liquid and gases. Here, when we heat a liquid, the bottom side that's getting the heat gain more kinetic energy. This side that is getting the heat gets more kinetic energy, so the liquid expand because you are heating. When you heat anything, it's expand. When you heat any substance, the particles they expand. The space is between the particles, not the particles themselves. The size of the particle remains same, but the space between the particles, they go further away from each other. That's what we mean by expand. So they go further. So when they expand, they become less dense. So the less dense one at the bottom will rise to the top, and then rises up again due to convection current. And this convection current is as a result of density difference. Density difference between the one at the bottom where you're heating and the one at the top. The liquid at the bottom and the liquid, they have different depth. Okay? The process continues till the whole surface of the liquid gain equal amount of energy, till you reach that level. But honestly, before you reach that level, the one at the bottom gain more kinetic energy, and then they expand, and then they become less gases. This is how conversion happens in liquid and gases. Now let's take a look at it properly. Explain conversions in liquid and gas. That's what we just explained, and the changes that takes place. Now let's take a look. How do liquids and gases transfer thermal energy? By conversion, and the process through convection current. Okay, by conversion. Now let's take a look at an example. Water. When you take water in the same liquid or within the gas. Okay, so this is how conversion happens. Conversion happens due to density difference. Because when you heat a liquid, the density of the one at the bottom becomes less dense. The one at the bottom becomes less dense. Why is it less dense? Because you heated it, they expand. When you expand, you become less dense. So you rise. The one on top is denser, falls to the bottom. So this is called convection current. The rise and fall of the liquid due to difference in temperature is convection current. And the whole process is known as conversion. This is how, when you boil water, this is how the thermal energy is transferred. Is that okay? This is how difference in density difference. Because of the difference in density. Because when you heat, the one at the bottom, the density becomes lesser than the one on top of the liquid, become less dense. You should be able to explain that. That is due to density difference. Now, how do liquids and gas transfer thermal energy? This is for gases. You have the insert stick and you have the smoke particle. Here we have 2 watts. Then you light up this insert stick, and then heat flow from here because you light it up. Then it flows to this one to light up this candle. This candle produces heat, and then the air here becomes less dense, and the air flow out here to this place, and then the denser air falls to this place and flow to this place. Like what is happening in air conditioning. When you put air conditioner in your room, okay, the air conditioner produces colder air that comes into your room, that fall out to your room. The room air is rises to replace the one air is about gas. This is conversion in gas. Sorry, not conduction. Conversion in gas. Okay, let's move on quickly. So this is explained here, what we have already explained. Now let's move to the next one. Okay, how do liquid transfer thermal energy? Liquid also, conduction can happen in liquid, but you don't do it from the bottom, because if you do it from the bottom, it will become conversion. It will be conversion, like we've explained in the past. So we heat from the top, so that this one will rise to the bottom. Okay, we rise to the bottom. The warm air pushes down through conduction till it gets. How do liquid transfer thermal energy? How do liquid transfer thermal energy? Okay, we say conduction in liquid. I think we've already explained this one. Conduction in liquid, which is not so very good. Okay, here you pause this video, you answer these questions, and so on and so forth. Now let's move to radiation. The fourth one is radiation. There are three methods of heat transfer. Okay, there are three methods of heat transfer: conduction, convection, and radiation. Conduction, convection, and radiation. We've explained conduction, we've explained convection. Now we're about to explain the third one, which is radiation. Remember, conduction and convection, they require heat, they require particles to carry out the energy, right? They require particles. But radiation do not happen in a vacuum, do not require any particle to carry out radiation. They do not require particles to carry out the heat, the thermal energy. Now, know that thermal radiation is infrared radiation, okay? And that all the objects emits radiation. All hot objects emits radiation, okay? All hot objects emit radiation. Now, thermal energy transferred by thermal radiation does not require any medium, does not require air particle, does not require solid particle, can go through a vacuum. So radiation is a method of heat transfer from through a vacuum, through a region without a medium, That's how the heat from the sun can reach us from the earth. Okay, can pass through space to reach us on earth. Okay, and also if you make a campfire, the heat can reach us. Can pass through medium, can pass through non-medium. Is that okay? So let's take a look at that quickly. Now, what's radiation? Here, the things that we expected, that the heat goes out in all directions. Like you make a fire, the heat energy is emitted as waves, as electromagnetic wave, which is called radiation, infrared radiation. Actually, we call it infrared radiation. The heat is emitted from all directions and to any neighboring substances, Now, let's take a look at radiation. Here, we describe an experiment to distinguish between good and bad emitters of infrared radiation. Now, let's take a look at, we already explained what thermal radiation is. We say a process whereby heat from emitting body, hot object, any hot object. It could be your bulb, your light bulb. It could be your fire you set. It could be the sun. Any hot object emits radiation, infrared radiation. And we say this heat can move through vacuum or non-vacuum to reach the destination object. And we said a good example is the heat from the sun. The heat from the sun reaches us through the vacuum and to reach the earth. And this process of heat transfer is called radiation. It's called thermal radiation. Now, here we want to look at objects that are good emitter and good absorber of thermal radiation. Now, we say thermal radiation, also known as infrared radiation. Thermal radiation, also known as infrared radiation. All objects absorb and emit infrared radiation. All objects, they absorb, meaning they take in, and they also emit infrared radiation. Even our body, they absorb and emit infrared radiation. Any object or all objects absorb and emit infrared radiation. Now, infrared radiation or thermal radiation, they are invisible radiation that carry thermal energy. If you're asked to explain it, infrared radiation are invisible radiation that carries what? Thermal energy. They are invisible radiation that carries thermal energy. Infrared radiation or thermal radiation, they are invisible radiation that carries thermal energy. Now, thermal radiation is the transfer. So if you're asked to define it, the definition will be thermal radiation is the transfer of thermal energy. Thermal radiation. We say thermal radiation is the transfer of thermal energy. It's the transfer of thermal energy. Thermal energy, remember, is just heat. We're talking about heat energy. It's the transfer of thermal energy in the form of invisible wave, which can travel through a vacuum. You can see the heat energy is here, the thermal energy. We dip it in a shiny silver thing. The dull black surfaces emit infrared radiation, right, at a faster rate than the shiny black surface. How do we know that? Because we connected to a computer and we plotted. Now take a look at this one. Is the shiny black. So the shiny silver thing. This one. While this below one is the dull black. What we did was to plot the temperature from this sensor. One below is emitting faster, which is for the dull black thing. It's emitting heat thermal energy faster than the one on top. The shiny black emits at a slower rate compared to the dull black surface. So what it means, a dull black surface emits thermal radiation or thermal energy at a faster rate compared to a shiny silver thing. Is that okay? That's what this one explains. Now let's go to the discussion is here. We can see. So, but we've already explained it. When objects emit infrared radiation, the temperature of the object decreases. Yeah, the one that emits, temperature will reduce because it has emitted thermal energy. So that object will cool down. Now, good emitters will give out infrared radiation at a faster rate. They will give out infrared radiation at a faster rate and cools down more quickly than the bad emitter. So this tiny black, because from the graph you can see it does it faster and at a faster rate, so it's a better emitter of infrared radiation. So it's a better compared to the shiny silver thing. Okay? Now to investigate this, we have to compare with two things that we have explained. Now let's go to absorption. The one we said just now was emission. Now let's take a look at absorption. We take a shiny, we wrap a temperature sensor we wrap it with a shiny silver foil, like aluminum foil, a shiny one, shiny color. We wrap it, and then we take a dull black foil and wrap this other temperature sensor and connect them to the data logger. The data logger is to plot the graph for us, to show us the graphical illustration. Now, if you take a look at this, you bring a bulb, a light bulb, it's providing the heat. We want to see which one will absorb faster. Is it this shiny dull black surface or the shiny silver foil? This is a direct graph now, a positive gradient graph. So since it's a positive gradient graph, the one on top is absorbing at a faster rate. So the dull black surface is absorbing heat energy from this bulb at a faster rate compared to this silver. This silver is absorbing at a less slower rate compared to this than black. So what it means, these two experiments, what they've shown us is that the dull black surfaces are better absorber and better emitter of thermal energy. The dull black surfaces, paper 4 questions. The dull black surfaces are better emitter and better absorber of thermal energy. However, this silver, shiny silver surface is a better reflector. For reflection, the silver one is better. This is what these two experiments has shown to us. We've explained this one, and let's move on to the next one. To investigate the absorption of infrared radiation through different surface, matte black, I think we've explained this already. Let's move on to the next one. Now, what are the factors that affect the emissions and absorption of thermal energy? There are 3 factors, okay? There are specifically 3 factors. One is the texture and color of the surface is one of the factors. Texture and color. Texture, I don't know if it will write for us faster. Texture. That affect absorption. The 3 factors that affect absorption. The 3 factors that affect absorption and emission. There are 3 factors that affect absorption and emission. One is surface texture and color. Okay, like we saw in shiny black, dull black, shiny silver surface and dull black surfaces. So you can see the texture and color is playing a role. And then number 2 is surface temperature. The higher the temperature, the faster the rate of emission, and faster the rate of absorption. And the other one is the surface area. The wider the surface area, the faster the rate of emission, and and so on and so forth. So these are the three factors. That's why marathon people who run the marathon race, once they finish, they are easily covered with something like looks like shiny silver, something to cover them to reduce the rate of emission of thermal energy from their body. Once they finish the marathon race, if you notice, they are covered with this. A marathon runner usually uses a space blanket. We call it space blanket to keep himself warm, to keep himself so that the thermal energy from his body will not be emitted quickly away from his body. So this space blanket will reduce the rate of emission. You can see it's a shiny silver surface to cover himself. So that's one of the factors. Okay, the second, we've also talked about the second factor, and the second factor is the temperature, surface temperature, and the third factor is the surface area. Okay, we've explained that. Now, he said explain the factors which affect the emission and absorption of thermal energy. I've already explained these three factors. One is the color, surface color and surface texture. That's why we choose a silver space blanket when you run a marathon race, because it will reduce the rate at which your thermal energy from your body is emitted from your body. The another one is the higher surface temperature. Okay, surface temperature. The higher the temperature, the higher the rate of emission, and so on and so forth. And you say higher surface temperature of object relative to the surrounding temperature, higher rate of emission equal to the higher rate of emission of infrared radiation. Right. You increase the temperature, the more emission will take place. Two objects of the same mass and material, but with different surface area. The third one is surface area. The one with the larger surface area will emit or absorb more infrared radiation at a higher rate. Okay, so that's for that now. The factors can be explained. What factors affect emissions? Still on that, by looking at room temperature and with the different object, the different temperature. At a higher temperature, the thermal radio, at a very high temperature, the rate of temperature is emitted and absorbed. Now let's take a look at this. How does the emission and absorptions affect temperature of an object? How does this? We say infrared radiation absorbed is greater the rate at which infrared radiation is absorbed. What is absorbed is greater than infrared emitted. What you are emit when the object, all objects they absorb and they emit. So when what you are absorbing is bigger than what you are emitting, then the object warms up because you have greater energy, thermal energy. Because what you are taking in is bigger than what you are giving out. So the object will warm up because there will be a positive increase in temperature. There is higher temperature as a result of that. Now, when infrared radiation is less than infrared radiation absorbed, the one that is absorbed is smaller, is lesser than the infrared radiation emitted, object will cool down because what you are absorbing is smaller than what you are emitting. You are emitting more, so you're losing more thermal energy than what is coming to you. So the object cools down. So infrared radiation absorbed is equal to infrared radiation emitted. In the test scenario, when the one infrared radiation absorbed is thermal energy absorbed equals to the thermal energy emitted. So the body is at equilibrium. Okay, let's move to the next one. How does the emission and absorption affect the temperature of the object? How does it affect it? You've heard of global warming, right? Now we say here, and the energy from the sun through thermal radiation reaches the earth. When it gets to the earth, it's emitted, right? Some are absorbed, some are emitted. The one that is emitted due to greenhouse gases, they are trapped by the greenhouse gases and they are trapped back to the earth to warm the earth. The one that's supposed to be emitted is reabsorbed back to the earth, making the earth to be warmer, hotter, right? So this is due to global warming. Global warming is causing what the effect calls the greenhouse gas effect. Natural process that warms up. Greenhouse effect is a natural process that warms the Earth's surface through a balance of absorption and emission of infrared radiation. Now, the sun gives us thermal energy, or what you call the infrared radiation. When they reach the Earth, some are absorbed, which warms the Earth, okay, which makes the Earth not too cold. And then some gases are in the atmosphere. So these gases will trap the one that is emitted that is supposed to go back into the atmosphere, and then they will redirect them back to the Earth to warm up the Earth much faster than it ought to have been. So this effect is causing a global warming of the Earth, making the Earth to be warmer, causing global warming, okay, due to greenhouse gases that we are releasing into the atmosphere. So here you pause this section and you solve these questions quickly. Pause the video and solve this question quickly. Now we go to the last but not the least, which is 10.5, which is applications and consequences of thermal energy transfer. Okay, quickly let's take a look at one method of thermal energy transfer is conduction. You know conduction, right? Conduction is one process by which we can transfer thermal energy. The one that requires free mobile electrons and lattice vibrations to carry out the thermal energy from the region from the hotter region to the colder region without the particle moving. Okay. Now, what are the consequences? Metal, they are good thermal conductors, right? Metals are good thermal conductors naturally. That's why we use them to make cookie pots, fry pots, and heating kettles, and so on and so forth. Now, they conduct thermal energy away from our body. They conduct thermal energy away from our body, making it feel cold. Okay, making it feel cold. Plastic, which are good thermal insulator, plastic, they do not conduct thermal energy away from our body. Okay, so as a result of that, application of good thermal conductor is that we use them to make cooking utensils. We use them to make cooking utensils. We use them because they are able to conduct thermal energy away from our body. So we use them to make cooking utensil and soldering iron for electrical work. Okay, to solder like copper, we can use it to make this thing to work electrically. So we use them to make pot, cookie pot, fry pan, and so on and so forth. Application of bad thermal conductors. The bad one, like the plastic, we use them to make, and wood, we use them to make the handle. You know, the handle is the one we hold. So we don't want it to be too hot. So we use the plastic or the woody one to make the handles. This handle we hold. So that's one application of this one. Okay, we use them to handle the handles of the cookie utensil. We use the bad thermal radiation to make them, and double glass windows to reduce thermal energy to our rooms. Screenshot is very bad. So in case of screen okay, now we move to one method of thermal energy transfer, conversion. Now conversion is used for land and sea breezes. We can use this one to explain that. During the day, the sea breeze, during the day, daytime, this is daytime, okay? During the day, the land is warm, so the warm air will rise from the land and move to the sea, while the cool breeze move from the sea to the land. So we call it the sea breeze. We call it the sea breeze. The sea breeze will rise, flow to the earth. That's during the day. That's why you see we have cool air around the beach area. Okay, the sea cool breeze will move to the land. But during the evening or night time, the land is cool. Okay, the cool breeze from the land moves to the sea, while the hot one from the sea moves to the land. So we have the land breeze. So conversion is this is conversion. Hot one rising, cold one filling the place. This is the consequence of convention, right? This is the consequence of convention. So what are the applications of conversion? We use them to make electric kettle to heat water, air conditioning to provide cold air to the room and absorb the warm air to the air condition, and also to make hot water radiator in cars, or hot water radiators in whatever we want to apply it to. Okay, now also radiation, we do this, what they call this farm. What do you call this farm again? There's a name for this farm. Greenhouse farm. Okay, we can use this one to make radiation, to make the greenhouse farm. Here, the infrared radiation from the sun travels through the vacuum, through the vacuum of space and the atmosphere to warm the earth. The infrared radiation from the sun travels through the atmosphere and space and everywhere to reach the earth and warm the earth. Earth's surface absorbs the radiation, warms up, and emits some of the infrared radiation back to the space. But these emitted ones, some of them are trapped due to global warming. The snow is melting at a higher or increasing rate. Snow is melting faster due to global warming. Reduced amount of radiation reflected from the earth also is being reduced, so they are trapped back. Okay, so one application of radiation is the greenhouse. One application is the greenhouse of radiation. So the heat from here trapped back in this green content, house content, back to this place to help this vegetable to grow, whatever you're growing to do well. Now, multiple methods of thermal radiation is a good example is the car radiation or the car radiator in our car. Okay, before we talk about car radiation, we also have one very important one, cooking, using firewood to cook. Using firewood to cook is one application of thermal radiation. The heat flows to the surroundings, or using firewood to warm the environment up. You know, in those days, we use all this. If you go to the West during the winter, they set firewood there. They have, what do you call that? Firewood something where they heat the house. Apart from heating, yeah, they have fireplace or fire whatever. They heat the whole house using this in the West during the winter. And in the car radiation, we also apply this thermal radiation for multiple uses. Here, we supply water to the engine, and this water is heated when this is hot. The vapor moves here to take out the heat here and brings it out, and the air flow. So fresh air goes in, get heated, and when it enters the engine, get heated, and then rises out, take out the heat, the thermal energy, and then cold one flows in. So it's a continuous cycle of what is happening. This is a consequence. So we pause the video, answer these questions quickly, and then with this, we've come to the end of our today's class. Thank you for joining us. Thanks.